In this video, we'll look at aggregate grading, which is an essential property as the base course relies on the correct mix of coarse and fine particles to form a strong interlocked layer capable of resisting the traffic loads without unraveling. As we mentioned in the introduction to roading, an aggregate is basically a mixture of sand and gravel. The mix of different sized particles is called the grading of the aggregate. The grading needs to fall within certain ranges to allow it to lock together to form a suitably strong layer. For example, a base course needs to have about 5 to 15% fine sand, 10 to 25% coarse sand, 25 to 35% fine gravel, and 45 to 55% coarse gravel to provide a granular layer that is strong enough to withstand the road loadings when compacted. This mix maximizes the amount of coarse particles in the aggregate with enough finer particles to fill the voids between those coarser particles. A grading test is undertaken to check that the different sizes of particles are present in the correct proportions. The grading is determined by passing the aggregate through a series of standard sieves. The sieving basically sorts the aggregate into different sizes. As you can see in the photo, the sieves are stacked on top of each other, with the coarsest sieve on the top and the finest on the bottom. Below the last sieve is a pan to collect the silts and clays that pass through this finer sieve. The stack of sieves is placed on a machine that vibrates the whole stack. That is what the mite machine under the sieve stack is. The top sieve, for a base course, has a mesh with 37.5mm openings, which means that any aggregate particles that pass through the sieve are smaller than 35.5mm across. The sieve sizes get progressively smaller, with the following sieves ranging from 19mm down to 0.075mm. The aggregate is dropped into the top of the sieves. This sieve stack is vibrated and the aggregate passes through the sieves. Particles that are larger than a particular sieve are retained on it, while finer particles fall through the sieve and keep on dropping through the sieve stack until they get retained on a sieve that they are too big to pass through. After the sieving is complete, we have 8 to 10 sieves, each with an aggregate of about the same size retained on them. The material that passes the finer sieve, the clays and silts, is caught in a pan at the bottom of the sieve stack. The aggregate retained on each sieve is then weighed and a percentage of aggregate passing each sieve is calculated. This is what we get. There is a separate file on Moodle showing how this curve was calculated, if you're interested. However, for this course you only need to be able to understand what the graph shows. The x-axis, that is the horizontal axis of the graph, is the sieve sizes. You can see the values calculated for each sieve size as dots. I have added labels showing some of the sieve sizes. The sieve sizes correspond to different types of soil, as shown by the green boxes. So the particles retained on the 2.36mm sieve and above are gravels, and those passing are sands, silts, or clays. Particles passing the 0.075mm sieve are silts or clay. Note that this axis is plotted on a logarithmic scale. I have added some additional values in blue to show you how it works. You can see that the numbers are not equally spaced. That is because a logarithmic, or log scale as it's usually called, is based on orders of magnitude rather than a linear scale. An order of magnitude is basically a scale of 10. So if a number is an order of magnitude above another number, then it is about 10 times bigger. You can see on the log scale that the orders of magnitude are evenly spaced. So there is equal spacing between 0.1, 1, 10, and 100, which are increasing orders of magnitude. The log scale allows us to view a wider range of values. In this case, the sieve sizes go from 0.075mm up to 37.5mm. That means the particles passing the finer sieve will be about 500 times smaller than those caught on the coarsest sieve. If we were to plot the x-axis to the linear scale, then the graph would look like this. You can see that half of the values are all jammed into a small part of the graph on the left-hand side, which does not give us a very good idea of what is happening in that part of the curve. Using the log scale allows us to get a good look at all of the values. The y-axis of the graph, that is the vertical axis, is a linear scale and has a percentage of the total amount of the aggregate sample that passes a particular sieve. So we see that 100%, that is all of the sample, passed the 37.5mm sieve, while just over 50% passed the 9.5mm sieve. The other 50% was retained on the 9.5 and 19mm sieves. The 9.5mm sieve marks the border between fine gravels and coarse gravels, so over 50% of the mix is coarse gravel. Remember that it is the coarse gravel that provides the primary support for the road loading, which is why it comprises such a big part of the mix. The other particles are there to fill the voids between the coarse particles and wedge them firmly into the base coarse layer. Some other things to note about the graph. Firstly, a steep slope, like the one between 9.5mm and 37.5mm sieves, indicates a large amount of aggregate is retained on the sieves. In this case, there is a lot of coarse gravel, as mentioned before. A shallow slope, like that between the 0.075 and the 0.6mm sieves, indicates that not much material falls into these particle sizes. The vertical distance between any two sieves tells us what percentage of the aggregate was retained on the lower size sieve. For example, the percentage passing the 2.36mm sieve was about 26%, while the percentage passing the 1.18mm sieve was about 18%. So we know that 8%, that is 26% minus 18%, of the aggregate was retained on the 1.18mm sieve. We can use this to determine the proportions of each soil type. So the sand is all of the material that passed the 2.36mm sieve, but was retained on the 0.075 sieve, 0.3mm sieve, and the 1.18mm sieve. The percentage passing the 2.36mm sieve is 26%, while the percentage passing the 0.075mm sieve was 5%. So we can say that 21% of the mix is sand, that is 26% minus 5%. The remaining 5% is silt and clay. So you can see that the grading curve provides quite a bit of information about the mixed particle sizes in the aggregate, which is important because subbases and base courses rely on having the correct mix to get a strong interlocked layer capable of resisting traffic loads. TNZM4, the base course specification, sets out the required grading for base course in this table. It sets out the minimum and maximum percentages allowed for each particle size. So you can see that the percentage of aggregate passing the 9.5mm sieve has to be between 43 and 57%. Note that the finest sieves are measured in micrometers rather than millimeters. The funny M-shaped letter stands for micro, which is 1/1,000,000th of something, and the M stands for a meter. So a micrometer is 1/1,000,000th of a meter. A millimeter is 1,000th of a meter. So a micrometer is 1,000th of a millimeter. In other words, 1,000 micrometers make up 1 millimeter. 1,000 millimeters make up 1 meter. So the 0.6mm sieve can also be called the 600 micrometer sieve, or for short, the 600 micron sieve. Another indication of the size of the micrometer is that a human hair is 60 to 100 micrometers in diameter, and the human eye can only see up to about 50 micrometers. Below that, you can't see it. We can compare the grading curve for the sample we looked at in the previous slide and see that all of the values fall within the minimum and maximum values required by TNZM4. So this aggregate meets the specified grading requirements, although it needs to meet the other requirements such as crushing strength, CBR, that we looked at before. We can also plot the maximum and minimum allowable values from the TNZM4 On the grading graph, the area between the two curves is called the grading envelope, and any grading curve that falls entirely within the envelope meets TNZ-M4 grading requirements. So looking at the sample we looked at in the previous slide, it fits entirely within the envelope, and so therefore it complies with the TNZ-M4 grading requirements. Note also that it is easier to see the fit on the graph rather than comparing values, so we usually use the curves when assessing the suitability of an aggregate. Let's look at another example shown here in blue. It goes outside of the envelope and therefore does not comply with TNZ-M4 and cannot be used as a base course. You see that over 65% of the mix is larger than 9.5 millimeters. So the problem is that there is too much coarse material. There is not enough fine material to hold the coarse particles in place. We would say this mix is too bony, which is a term used for too much coarse material. Let's look at another one. The orange curve shows the opposite case where there is too much sand, and so the aggregate is not suitable for use as a base course. There is not enough coarse material to provide the primary support for the traffic loadings. Lastly, purple curve fits the envelope except for having too much fines to the left. In particular, the amount of material passing the 0.075 mm sieve is 15%. This material is silt or clay, which can weaken the subbase if there is too much of it, which is the case here. We discussed the problems with silt and clay in the fine materials testing video.